All right, everyone. How are we doing today? Doing okay. I'm recovering a little bit. Yesterday was an interesting day. I had to do a lot of running around, and it kind of unsettled the rest of my schedule. So I'm uh, trying to get all that taken care of. Administrative things that I need to do to keep all the plates spinning for the week, and I didn't get to work on that stuff yesterday. Is the main deal. But anyway, I'll hopefully get that sorted out. And the plan for today is to continue on in chapter 13. We have two more sections left, which we should be able to get through today and on Friday. As you can see, today we're going to be talking about arc length and curvature. So we're going to continue working with some of the details of space curves. And so let's get into it. All right. So for the length of a curve, this is something that came up back in Calculus 2. If we had a parameterized function in terms of f and g, we could use this expression. Now the idea here is that in this case, we have some curve in two dimensions that we think about as being the collection of all points that satisfy this relationship. The x-coordinate is given by f of t, and the y-coordinate is given by g of t. Okay? So this would be in our current understanding, a 2D space curve, right? Or a plane curve is how we would think about this these days. But we had this formula back from Calculus 2, and there were a couple different ways that we could write this down. Sorry, I'm going to write that bigger. Okay. And if we have the parameterized version of the function, we could use Leibniz notation instead of our function and prime notation. But it all means the same thing, all right? Now, if we extend this to 3D, there isn't any extra work to do, okay? We just make it bigger. Sorry, there was a prime here that I forgot to write. That's gonna bug me. Okay, hold on a second. My driver on my thing freaked out for a second. I'm gonna have to close and reopen the program. Where's my mouse? There it is. I think we're back now. Sorry about the trouble there. Okay. I think we got it fixed. Put that prime back in there. Okay. At any rate, we just add the missing coordinate to this expression. So we'll put these in blue so it's clear what we added. Okay. We just add the extra term. Now, the real way to think about this is, instead of trying to keep track of how many terms we have, is to, in general, think about how we would want to measure distance along a curve or arc length for any number of dimensions, if we're talking about Rn, right? An n-dimensional real vector space. So the expression that we're going to think of instead is, if we have R of t and we have our parameter functions, and there could potentially be any number of these, right? Okay, there could be 2 of them, there could be 50 of them. All right, the idea behind what I'm about to write is the same. What we want to do is compute the magnitude of the derivative of this vector function. Okay? And this formula is exactly what we had for our integrand. It's the square root of the sum of the squares of the derivatives of the components. Okay? Now, this way of thinking about this works regardless of how many components I have. So when I remember this, I don't try to remember a 2D formula and a 3D formula. I just remember the fact that what I want is the magnitude of this thing, and that tells me the integrand for my arc length formula. And so what we get is this. Arc length is defined as the integral from a to b of the magnitude of r prime of t dt. Okay. Now, in some other places, you might see the double magnitude bar for norm instead of the single magnitude bar, which is what your textbook uses for this. They mean the same thing. Okay. So just as a reminder, because if you look this up in other places, they might use the alternate notation. When you see that kind of expression, some quantity in between those double magnitude bars, that's referred to as a norm. All right. So as a visual representation of what sort of thing we're talking about, What I'm imagining is that I have some kind of curve. Okay. Make it a little bit better drawing. Okay. And the length of this curve is how much ink, so to speak, it takes me to draw that curve. That's what I'm measuring. Okay. If this were a path or a highway, okay, how many miles would I put on my odometer traversing this path? And the way that the integral construction works for this is that we are thinking about breaking this up into little line segments. Along the curve here from point to point. Okay, I'm not going to draw all those. And because we think about integrals as summations, the idea is that we end up with more and more shorter line segments and take the limit as the number of line segments goes to infinity. Okay, and then that sum in the limit converges to the arc length. That is ultimately what this formula does, right? Each individual line segment would be the distance from r prime of t naught, sorry, would be the distance from r of t naught to r of t naught plus h, right? And we measure that distance and multiply it by delta t. So we get a bunch of line segment lengths. Yes?
So would your A and B values be the values of t that creates those two points of the line?
Yes, that is correct. Down here we would have t equals a, and up here we would have t equals b. Yes. The question, sorry for those of you in the chat, was about the limits of integration and how they're interpreted. And then obviously if I were looking at some smaller segment of the line, say t equals alpha or t equals beta, then I would write that. Okay. So let's do an example. Okay. So we want to find the length of the curve. R of t equals t 3 cosine times 3 sine from -5 to 5. Okay. What we need to do first is compute r prime of t. I'm going to go ahead and move this to the next page of the notes because I know I'm going to run out of space here. Okay. Right. All right. Sorry. There's some of the, I have shortcut keys on my tablet that I write on, and I was trying to remember if I had a key for cut. I don't think I do. Anyway, that's fine. Okay, so the first thing we want to do is compute each of our derivatives here. Derivative of t is 1. The derivative of cosine is negative sine. And the derivative of sine is cosine. So we get this expression here. Okay. The next thing to do is to compute the magnitude. So we get the square root of 1 squared plus negative 3 sine t squared plus 3 cosine t squared, all under the square root. This is going to give us 1 plus 9 sine squared t plus 9 cosine squared t. Cosine squared plus sine squared is 1. So our integrand here is very, very simple. Square root of 10. If I did something wrong, tell me. I see people making faces here in the crowd. At least I think I see you're making faces. You got masks on. Okay, so the step that I skipped was factoring. Well, it's fine. I didn't write it down. Okay, anyway. There's a weird balance to be struck when you're doing this in front of other people. Is I need to show enough so that you can follow what I'm doing, but not enough that we waste a bunch of time, right? So anyway, questions are fine. Okay, so we have the square root of 10, and now what we want to do is look at the value of the integral from negative 5 to 5 of the square root of 10 dt. Okay, they're not always going to be this easy to integrate, but I wanted to put into practice what it is we're doing. We integrate a constant, we just multiply by t, we evaluate from negative 5 to 5, and the answer is 10 radical 10. So we get 5 radical 10 minus negative 5 times radical 10. I'm sorry, what? We did a two-dimensional version of this. Okay, that's why at the beginning I wrote down the 2D formula and then expanded to 3D. We're retreading some stuff. The difference is that we're now using vector notation to describe the ideas, and the new stuff really is the step beyond, for the arc length computation. Okay, so arc length should feel familiar. I'm glad that we're turning on some maybe dormant brain cells. Things reminding us from a semester ago, or maybe longer, depending on how your schedule's worked out. Okay. Get everything organized here. Okay, so the only thing that can happen in terms of an arc length question is I give you something that's harder to integrate from this point on. Okay, something to keep in mind is that because we have integrand expressions that involve square roots of things squared, it isn't terribly uncommon for us to find ourselves in a situation where we have to do trigonometric substitution in order to do the integral, because that's the pattern that those things follow, right? So when you're going through and working on your exercises and practicing things so that you can do these computations, make sure that you do a couple problems that end up that way, all right? That is not something that you want to allow yourself to be ambushed by on an exam because you only did the questions that showed up on the quiz, or you didn't do enough of the homework or something like that, okay? It is definitely part of it, and you should make sure that you're prepared for it. All right. Okay. One of the things that we can do for our curves is parameterizing the curve with respect to the arc length. Okay? We have our function t, which is the value of the parameter that tells us what the inputs are for the curve, right? But another way to, something to realize about what's going on here is that traveling along the curve isn't done on a one-for-one basis in terms of t, right? I could have a curve that looks like t squared, t cubed, okay? And as t changes, I'm moving 1-to-1 with t in the x direction, t squared in the y direction, and t cubed in the z direction, okay? So the scaling of how much I'm moving in each dimension is wonky depending upon what exactly this expression looks like, okay? If I want the version of the parameterization that actually tells me on a one-to-one basis how far I have traveled along the path itself, that requires a parameterization with respect to arc length. Okay, I don't get that for free. That's not t, it's a different variable. Okay, the way that we would define something like that is by defining an arc length function. We tend to use the variable s when we're referring to arc length. The reason for that is this formula for the arc of a circle. Okay, that's where the s comes from. Sorry, let me. Now we have to be careful about our letters here because I have to use a dummy variable. Okay, so that's tau that I used as the variable of integration. It's a funny looking t. It written bigger looks like this. Okay, it's kind of a like squashed backwards capital J. I forgot one of my magnitude bars. Sorry about that. Yes. It is d tau. Okay. So the thing that's going on here is that I want to integrate along this curve from t equals a, or sorry, from tau equals a to tau equals t. Okay? So I'm moving along the curve in that fashion. Does that make sense? Okay. So that's what this integral is describing. In order to make that work, I have to have different letters that shows up on my limits of integration and for the what the dummy variable is for the integrand. And what this does is it gives me a variable s that I can use in order to express what's going on with my function. Okay, so what will happen is I will get some formula that depends on t as a result of computing this integral, and then that will be a function of t, and then I can relabel and then use s and figure out what s is in terms of t, and then rewrite my vector function using the variable s instead of t. So what that would look like let's use the example that we just did. Okay. So let's take the example from here, except instead of going from -5 to 5, we're just going to go from 0 to t. All right, to simplify the formula. So we're going to say that s of t is equal to the integral from 0 to t of the magnitude of r prime dt from our previous computation. Sorry, I wrote dt. I should have written d tau. Okay, and if the tau bothers you, pick some other letter. It doesn't matter what the letter is. I'm just using tau because it looks like t, but it's not t. Okay, so we have this expression. I evaluate the expression from 0 to tau, so I get radical 10 times tau minus radical 10 times 0. So I'm left with radical 10 times t. I'm after plugging in the t. And so what this tells me is that s is equal to the square root of 10 times t. And then I can replace t in my vector function by s here. Was it sine then cosine? Yeah, or cosine then sine. All right. Okay. Now what this does is it tells me that as I vary s, I'm getting a one-to-one correspondence to traversing along the curve. So if I draw this function, which the sketch for this thing, I want to make sure that I get it right. This is 3, I know it's 0, right? Yeah. It's a helix coming towards us. Okay. And parameterizing it in terms of arc length means that s increases at a one-to-one rate as my pen was moving, drawing the curve. Okay. It's obviously, for this function, pretty close to what it was previously. but we have to compensate for the fact that this stuff is moving on a circle, right? In order to have the scaling work correctly with sine and cosine. Yes. These are all S's. Yeah. Sorry. Sometimes I write small when I write too fast. S is the arc length. Okay. So the way that it works is we think about the functions as being depending upon t, right? But t can just be t is just some variable that we pick to make the formulas easy to write down. Okay. What we do with s is that we specifically pick s so that s is exactly the measure of distance along the curve if I'm walking the path. Okay. So s is a variable that serves a similar role to t in that it gives me a way to describe what the curve looks like, but it is specifically scaled so that it is 1-to-1 with the distance traveled along the curve. Okay? If I don't do anything special to t doesn't guarantee that I get that. Okay? Because I can be moving more in the x direction than I'm moving in the y direction, and that messes up the scaling. Using this formulation for s brings everything in line so that it's all 1-to-1 with respect to the frame of reference of traveling along the path. Okay, until I make this parameters, until I use the arc length parameterization, t is just some variable that tells me how to write down the functions. There's nothing special about it. Okay. All right. So the next direction that we need to go is working with our tangent vector function, which is r prime of t, and using that to describe curvature. Okay. So we want to start talking about curvature. And this is one of the things that I don't know if your calculus teachers previously had mentioned this when it comes up in Calc 1 and Calc 2, but we kind of on purpose go out of our way to not talk about curvature in those classes, right? If we were describing some function that looked like this, okay, we would make some noises about maybe this being concave up and this being concave down, right? And then this also being concave down on this other side here. But even though it looks like curvature, or our kind of vague notion of curvature would have something to do with how this description works, we don't talk about it, okay? And the reason is that the information that's being conveyed by whether or not a function is concave up or concave down is separate from the kinds of things that we mean when we want to talk about actual curvature, okay? Curvature is more complicated and is very difficult to discuss without bringing in concepts like arc length and the vectorized versions of functions, okay? And because we on purpose avoid the vector versions of the notation, we can't introduce the necessary notation and vocabulary to talk about curvature. So that's what we're going to do now. Okay. Now, one of the things that we do need for curvature is the idea of smoothness. Okay. Now, the word smooth, as I hope you were all told in your previous calculus courses, refers to the function having continuous derivatives. Okay. So when I use the word smooth in a mathematical context, it is a reference to the function having continuous derivatives. Okay. For our purposes, one continuous derivative, which would be described like this, okay, C1 on some interval. This is, if a function is a member of this set, it means that it has one continuous derivative on the interval from a to b, at least. Okay, it can have more continuous derivatives on that set, but it needs to have at least one. Okay, if we change this value to something else, then that would mean that whatever functions we're talking about have at least 3 continuous derivatives. Okay, and that counts for each component function. So each component function must have at least that many continuous derivatives. For those of you who have taken or will take someday differential equations, this notion of smoothness is really important, right? Because if I have a second order differential equation, which is a differential equation that has 2 derivatives in it, whatever solutions I come up with for that differential equation needs to be of class C2, because I need at least 2 continuous derivatives in order for my expression to make sense, right? So this is notation that you will either have seen before or will likely see moving forward, okay? So if we are looking at this expression here, and we have some kind of curve, we of course are thinking about there being a bunch of tangent vectors pointing off of this thing, right? There's a tangent vector at every point. And what gives us the notion of curvature is how much deflecting is going on in these tangent vectors as I traverse the curve. Because the curvature is in terms of what's happening with the tangent vectors. In order to measure this, there are a couple of different formulas that the textbook provides, okay? The letter that's being used here is kappa. Okay, it's a very tiny kind of scrunched capital K looking shape. The first formula they give is the magnitude of dt ds. So the magnitude of the derivative of the unit tangent vector with respect to the arc length parameterization. Okay, as a reminder, the unit tangent vector, is the tangent vector divided by its length. Okay, so the normalized tangent vector. Now, if we write out this expression, we can come up with a different version of this formula here. It's probably, in practice, easier to use. But it does require that we compute some magnitudes of things. Okay. we can get the formula for curvature in terms of the derivative of the unit tangent vector function and the tangent vector function. Okay, so a little bit of calculus to do in order to come up with those formulas. But what this will give you is a formula in terms of t that tell you what the curvature is for a particular value of t. All right. And then there's also a third formula, because why not, right? This is a pick your poison scenario. If you like cross products, maybe save yourself a little bit of effort by using this version of the formula. Okay, so the options here are find this, which is not practical most of the time. Okay, you can compute this version of the formula, and computing this version of the formula involves finding this expression exactly as written and then computing its derivative. Okay, that includes dealing with whatever nastiness comes out of this denominator. Because you have to do it in terms of t. You don't get to plug in any numbers. You have to take the derivative before you plug in anything for lowercase t. All right, so it could be algebraically a problem. All right, this thing looks worse, but it's probably the easiest one to work with. Okay, all you need to do is compute the first and second derivatives of r. Okay, compute a cross product, which is just a process, right? You're not going to have to worry about any weird integrals or tricky algebraic substitutions or nasty quotient rules or things like that, right? Because you might have to do the quotient rule here. And then for this thing, you just compute that, and then you'll have an expression in the denominator. Okay. Now, we're a little bit short on time, and there are a couple of other ideas that I need to make sure that we talk about. So I will let you check out an example of computing this in the textbook and work on the homework and stuff. If you have questions, of course, we can talk about those in class next time. Okay, but it's a computation problem. I want to work us through the ideas of everything. Okay. All right. Okay. Now, in addition to the notion of a tangent vector, we also have a normal vector and a binormal vector for traveling along our space curve. So if we have some axis and we have some space curve here, if I pick a point on the space curve, there are three vectors that I can think about. Okay, I can think about this vector which is the tangent vector, and we're going to normalize it so that it's a unit tangent vector. Okay. I have a vector that points, getting the perspective on this right, it's going to be a little bit difficult, okay? But I have a vector down here that is the normal vector. That depends on t. And then orthogonal to both of these, and this is kind of pointing away from us into the screen, is a binormal vector, okay? So at some point on the curve, I have three mutually orthogonal vectors that look like they form a coordinate system that's sitting on the curve. This one here, that's in the direction of travel of the curve, and then to that point perpendicular to that, and that are perpendicular to one another. Does that make sense? Okay, so one of the ways to do this is if you remember the right-hand rule, okay, you can make the finger gun thing, right? And with your right hand having made the finger gun, you think about your index fingers pointing in the direction of the path as you're traveling along, and then your index finger and your thumb give you the position of the normal vector and the binormal vector, right? And if you imagine tracing a path with your hand, you're going to see how these things turn in space as you have to turn your wrist to keep your finger pointing along what would be the tangent direction of some path. Okay, so you have your thumb, you have your palm turned in to the way that you think that the path is curving, right? And obviously your arm can't articulate enough to be able to do like loop-de-loops as you're traveling along a path, so it's not exactly perfect, but that's the idea. Okay, that's what the binormal vector and the normal vector and the binormal vector are doing. They are the paths or the vectors that are represented by your index finger and your thumb, or your middle finger and your thumb. Okay. Now, the way that the normal vector works is the normal vector points inward with respect to curvature. So if I have, say I just have a circle in the YZ plane. Okay, so this is a circle in YZ plane. The tangent vector, assuming this orientation for the circle, the tangent vector points this way, right? The normal vector is going to be the one that points towards the center of the circle. Okay? And then the binormal vector would point this way, either towards us or away from us, depending on how things are oriented. I guess, sorry, it would be towards us. Yes. Okay. Now the formula, and I know that we're close to out of time here. The formula for the normal vector, which is the one that we tend to work with, is given as Sorry, I didn't mean to put the magnitude bars in the numerator here. Let's paste. Okay. So someone asked if the normal vector was like the acceleration vector, and that is correct. Okay. We have the unit tangent vector, and we take the derivative and normalize. We take the derivative of the unit tangent vector and normalize it, and that gives us the normal vector. All right. So the tangent vector is the direction of the velocity. It is not the magnitude of the velocity, okay, because we normalize it, right? The normal vector tells us the direction of acceleration for the curve, okay? Assuming that the curve is turning, okay? The curve may not be turning. If it's going straight, then it would be potentially accelerating in a straightforward direction, right? So there has to be some off-axis action there in order for that to be an exact analog, but that is a helpful way to think about it. Okay. There's a little bit more geometry that we can add to this, but we're out of time, so I will try to work that in tomorrow when we're discussing in more detail motion in 3D space, and then try to connect to these ideas, the physics ideas that some people were starting to ask about. But we're now at the point where we have enough of the framework to have that discussion. So take care, everybody. Have a great one, and I will see you next time.